So far we have seen two operations that are push and pop operations. Push operation basically added the new value at the tail end of the singly linked list, and pop operation basically deleted the value from the end of the singly linked list. That is, basically we have deleted the very last node, right? So by implementing these two operations, basically we have performed the addition and removal operation on a singly linked list at the end of the singly linked list. What if we have to perform the similar operations on the beginning of the singly linked list? That is, if I have to add a new value at the beginning of the singly linked list, or if I have to remove the value from the beginning of the singly linked list. Now let's get on to implementing such functionalities. So the functionality which basically adds new value in front of the singly linked list is basically nothing but a unshift operation. So as part of unshift operation, what we will exactly do is we will take the value from the user and we will basically create the node object with the value that user has given, and we will make sure that this node is getting added at the beginning of the singly linked list. Okay, just remember that unshift operation is used for adding the value in front of the singly linked list. So we already have head node and tail node and length inside our singly linked list representation, right? Since we are adding the new value in front of the existing head node, whatever the new node that we are adding will get added here. Okay, so we have to make sure that whatever the remaining singly linked list is available already, we have to make sure that we are keeping the track of the next pointer of the existing head node inside the new node that we are adding. Okay, so that is a simple shift operation. That means we will basically add the new value in front of the existing head node of a singly linked list. So what all are the different cases that can come while performing the unshift operation, right? Obviously the first case is when the singly linked list is empty. When the singly linked list is empty, right, whatever the head comma tail that we are maintaining, they both will be equal to null or none based on our programming choice of implementation. If we are simply implementing it with Java or JavaScript, we are maintaining null in head and tail, and we are maintaining none in head and tail if we are choosing a Python based implementation, right? So since I'm making this course as a programming language agnostic course, so I'm trying to explain it for all the languages here. And inside the length, we are having 0. Now whatever the node that we are adding, right, since the singly linked list is empty, whatever the new node with the value that user has passed, let's say 10 here, that will become the head node and tail node, right, and length will become 1. So since the singly linked list is empty, we know how can we check a singly linked list is empty, right? Using that logic, we will obviously check the singly linked list is empty or not. If it is empty, we will update the head and tail with the new node that is getting created with the value that user has passed, and we have to make sure that the references are getting updated properly as well. In the end, we will increment the length by 1. Now let's try to handle the second scenario where the singly linked list is non-empty. That means that we have certain number of nodes available inside the singly linked list. Now our aim is to add the new node in front of the singly linked list. That means we will have to add the new node in front of the head node that we are maintaining. Let's assume that in that case the singly linked list has some, let's say 3-4 nodes available inside the singly linked list, right? And we have the head node and we have the tail node. Let's say 10 code and true are the values that are present inside the singly linked. Now let's assume that user has given one string by the name, let's say false. Okay, now our aim is to insert this false or perform unshift operation using that false in front of the existing head node. That means false, we will create the object, right? So we will create the node object, and inside the false node we have to have the next, right? And that next we will update it with the existing head node of the singly linked list. In that way, we are not losing the remaining singly linked list that we already have. So we have to make sure that the next of the newly added node is getting updated with the reference of the head node. Okay, because head node is the next node of the false, because we are adding a new node in front of the singly linked list. And if you observe here, right, whatever the head node 10 that we had earlier, this will no longer be the head node of the singly linked list. So the head node will be the newly added node on a singly linked list. So we have to update the head to the newly added node on a singly linked list. And we also have to make sure that the length also getting incremented by 1. Okay, we have to increment the length by 1, because after all we are introducing a new value into the singly linked list. Okay, these are the two scenarios that can come when we are performing the unshift operation. Okay, when we tried performing the push operation, we tried adjusting the tail end because we are adding the new value at the tail end of the single linked list. Now we are trying to perform the new node addition operation in front of the head node. So we have to make sure that the necessary changes are being tracked inside the head node and tail node and length appropriately according to the case that we have discussed. Okay, so that is how we perform the unshift operation. Now we have seen the different cases that could arise when we are performing the unshift operation, right? According to that, let's write the pseudo code for the unshift operation. So what exactly we will do here? Here we will basically take the or write the function called unshift function, and it will basically take the value that user wants to add in front of the head node of the single linked list. As part of this implementation, first what exactly we will do is we will create the object of node with value that user has passed. Okay, so we will assign it to some variable. I mean, you will exactly see how we are storing it in some variable in the implementation, right? So since this is a pseudocode, let's just try to put our algorithm into terms. And after creating the object, first what exactly we will do? We will check if the singly linked list is empty. If the singly linked list is empty, so what exactly we will do? Whatever the node that we are adding will be the only node that will be there inside the singly linked list. That's why we will update the head with the new node that we have created with the value that user has passed. And since that is the only node, tail node will also be pointing to the same node object that we have created. And length we will increment by 1, length plus 1. In the end, we will simply return the new node object. Okay, because that is the node that we are adding. Otherwise, what you can do is you can also return the head node which contains the new node that we have added as well. Okay, so this is the pseudocode where we are trying to handle the case where we don't have any nodes inside the single linked list when we are trying to perform the unshift operation. Similarly, let's just write the otherwise case. That means that single linked list is not empty. So if the single linked list is not empty, what exactly we will do is first we will read the head node. Okay, just read it into some variable because we have to use that node as a next reference in the new node that we are adding. So update next of new node that we created with head node that we read. So inside the node that we have created with the value, we have updated the next reference. That means that the connection has been established with the remaining singly linked list. And if you observe the logic that we discussed earlier, right? So whatever the node that we are adding will become the new head of the singly linked list. That's why we have to update the head equal to the new node that we are adding. In the end, we have to increment length by 1. Okay, so that is how, I mean, before closing this, we have to return the new node that we have added. Otherwise, since the head node will contain the, I mean, whatever the head node that we are maintaining inside the single linked list will contain the new node that we are adding, right? Because we are making sure that, since we are adding the new value in front of the head node, we have already updated the head node. We can return head node as well instead of returning the new node object. Okay, it is up to your choice. Okay, so that is how we exactly write the pseudocode for performing the unshift operation, or the operation which basically adds a new node in front of the existing head node of a singly linked list. Okay, now let's go ahead and let's try to implement the same thing programmatically. So in the existing singly linked list implementation class that I have written, in here I will be writing a new function called Unshift. Okay, it will basically take the value that user wants to insert in front of the existing head node of the single linked list. So here, if you remember the algorithm or pseudocode that we've discussed, whenever we are trying to add a new node in front of the existing head node of the single linked list, there are two scenarios. One is either you're trying to perform the insert operation in front of the existing head node in an empty single linked list or a non-empty single linked list. So to support these two cases, if we can write the JavaScript implementation, we would have successfully implemented the unshift operation. So now let's try to write the logic which will honor these two scenarios. So first what I will do is, we need to insert a node with the value that user has passed, right? So what I will do in the beginning is, I will create a new node with the value that user has passed. So I'll create a variable called new node, and let me just create the object of node with the value that user has given. Now, as part of the first condition, let me support the logic for performing unshift operation in an empty single list. So how will we know if the single linked list is empty? If either head is null or tail is null, or you can also compare if length is also 0, then we are sure that there are no nodes in the single linked list. That means whatever the single linked list that you're trying to use for unshift operation is basically empty. So in that case, whatever the node that we are adding, that itself will become the head node and tail node, right? So what we will do, we will simply update this dot head to new node that we have created, and this dot tail also to the new node that we have created. Okay, we have successfully updated the head and tail references of single linked list implementation to the new node that we have created. Okay, in this case we have honored the first scenario where we are trying to perform unshift operation on an empty single linked list. Now if this is not the case, that means if the single linked list is not empty, that means it has at least one value. In that case, we already have the head node reference, okay, in this dot head, which will basically contain the entire single linked list, and we have also created a new node. So in this new node we have the next, right? If we can simply assign the head node to it, we would have adjusted the next connection of the new node, and we would have had the access to the remaining single linked list as well. So to adjust that, what we will do is, we'll simply take new node, this node's next, I will simply update it to the existing head node, that is this dot head. Okay, once we have done this, we would have added the head node. By doing so, we would have added the entire single linked list to the new node that we have created. Now here we have successfully added a new node in front of the head node. So whatever the new node that we have added will be the head node of the entire single linked list. So we have to update this dot head should be new node that we have added. Okay, don't forget that here. Okay, if you forget that, even though you have added the new node, we would always start from the old head that is available in the single linked list. So this update operation is very important. You should not miss this. Okay, in either of these cases, right, we are basically adding or introducing one new node into the single linked list. That means length should be incremented by 1. So what I will do, I'll simply update this dot length to this dot length plus 1. Okay, in the end we will have to return the new node that we have added, that is nothing but return new node. Or also you can also, that new node is like a head node right now, right? You can also do this dot head also, either of them are just fine. Okay, this is how we perform the unshift operation. Now let's just try to call this function and see if we are able to validate the result. Let me just comment out these lines. Okay, let me just remove these lines of code as well. Now after the pop function, let me just take SLL dot unshift. So if you see here, right now we have 4 values. The head node is 10 and the tail node is 10.134. If we try to perform unshift operation using a new value, let's say SLL is new string that I want to insert in front of the existing head node. That is, right now head node is 10. If we insert this value in front of it, the resulting list will be SLL 10 codingpal.org true 10.134, right? So if we try to print the values of head node, tail node and the length also, you should see the reflected results. So in the terminal, what I will do, I'll simply try node. Okay, this file is inside the folder singly linked list, right? So singly linked list.js. If you observe here, the SLL is being added into the singly linked list and is the new head node of the singly linked list. Okay, that means we are maintaining the consistency across head node. And the tail node is 10.134, which is correct, and total number of nodes are 5. So before performing unshift operation, we added 4 nodes. By adding SLL into the linked list, singly linked list, we have total of 5 nodes or 5 values in the singly linked list. Okay, this is the case where we try to perform unshift operation on a non-empty singly linked list. Let me just comment out these push operations in the beginning. Now we are trying to perform a unshift operation on an empty singly linked list because there are no values at all. So there should be only one value, and that one value is SLL only. So head and tail also will be same. So if I simply run the command again, if you see here, as part of traverse function, we printed SLL, and as part of these lines of code, we have printed head and tail and the number of nodes or the size of the singly linked list. So which we've got SLL, which is the head and tail 2 in the singly linked list. So if you observe here, we are maintaining the consistency across, all the cases for head and tail nodes in the singly linked list, also for the length too. So that is how we actually perform the unshift operation, or we try to add the new node in front of the existing head node of the singly linked list. Okay, I hope you are able to understand and implement along with me. If you have any doubt, go to the codingpal.org, especially go on to singly linked list implementation, go to the visualization panel and try to visualize this for various scenarios with different inputs so that you will have a better understanding. Okay, after this, try to perform unshift operation with multiple values, follow the algorithm that we have and try to identify the possible output. Okay, that is the best way for understanding any of the operations that we are trying to implement. Now that we have implemented the unshift operation on a singly linked list, let's try to analyze the space complexity and time complexity involved in this unshift operation. So obviously, let's just try to talk both of them in terms of best case as well as worst case. So obviously, in performing the unshift operation, there will not be best case or worst case. Usually people will think that when there are no values at all inside the singly linked list, there will be best case, and the worst case is obviously when we have n number of nodes inside the singly linked list, right? So in both the cases where the singly linked list was empty, if it is empty, we have updated the head node and tail node with the new node that we have created with the value, and these are simple assignment operations, right? In that case, obviously simple assignment operations will take constant amount of time. As a result, in the best case scenario, the time complexity is order of 1. Similarly, if we have n number of nodes as well inside the singly linked list, what exactly we did? We simply created the new node object. Okay, previously we had head this and we had tail here, and we simply created the new node and we simply updated the next of newly created node with the existing head node. So that is also a simple read and assignment operation, right? So we know those operations will take constant of amount of time only. As a result, and even if you have n number of nodes on which you are trying to perform the unshift operation as well, the time complexity will still remain order of 1 only, even in the worst case scenario. Okay, so there is nothing like worst case or best case. Both, all of them are best cases only in the way we are implementing the unshift operation. Now let's talk about the space complexity. Obviously, when we had no values inside the single linked list, we are updating the head and tail and we are incrementing the length by 1. So those operations are simple assignment operations, right? As a result, the space complexity will also remain inside the best case scenario. When we have worst case scenario also, we can directly read the head node, because inside the single linked list representation that we are doing, we have the head node, tail node, and we have the length as well. So all we have to do is we have to read that head and we have to assign it to the next of the newly created node. So obviously these read operations will take only constant amount of memory, and in the end we are updating newly added node as a new head of the single linked list, right? As a result, that operation will also take constant amount of memory. As a result, overall space complexity will be constant, that is order of 1 only, even in the worst case scenario. Okay, so that is how we exactly perform the or calculate the time and space complexities involved on a unshift operation.